All right, everyone, welcome to our second week of the graduate seminar in Math E15. Today we will finally get to use, or start to use, the real epsilon delta definition, as it's called, of the limit. Remember, last week we focused on just understanding what we mean by a limit, which was that as x gets closer and closer to whatever c value we're talking about, the y values get closer and closer and closer to whatever L value we're talking about. But it was just a completely informal definition that we had last week because we had lots of words in there that weren't really good math words. So now we have the real definition. So by the way, we are using the handout called Day 2 from the course website. We'll also be using an applet today, which you can also find the link to on the course website. Here is our definition. This is the big one that took generations of mathematicians to come up with, as we discussed last time. It's got a couple Greek letters in it, but they're there for a reason. We'll talk about that. And these are the letters that everybody uses, so there's no getting around using these Greek letters. So in general, there's a lot happening in this definition, so we'll take it slowly. And we're going to do a bunch of examples today. Our goal today is just to understand this definition. So we say the limit as x approaches c of some function f of x is L. What does that mean? It means that for any or for each, and this is the Greek letter capital epsilon, for each epsilon greater than 0, there is a delta greater than 0 such that if 0 is less than absolute value x minus c less than delta, then absolute value of f of x minus L is less than epsilon. Okay, there's a ton of things going on in that definition. So let's try to look at a picture here. So here is my function that I've drawn, and I think the limit is L. And this is c. This is where I'm interested in trying to find the limit. So let's start with this Greek letter epsilon. The reason that this is the particular Greek letter that was chosen is because it's like our word for error. So you can think about epsilon as an error bound that you have to make the function stay within. So what this is saying is that the reason that we use absolute value is because we're trying to measure a distance. And when you're measuring the distance between two numbers, absolute value is the way to do it because that way you don't get any negatives. So this is saying the distance between f of x and L must be less than epsilon. In other words, if I start here at L, I can go up epsilon away from L, and I can go down epsilon away from L, and my function f of x is supposed to stay inside this little epsilon band. I do that by choosing a delta. Question?
I don't understand how Epsilon Band thing you just said just now.
So let's maybe look at this then for a second to understand the epsilon band. So if we do a specific example here, suppose that x is approaching 3 of f of x equals 5. Let's suppose that that's what this limit is. And we're given epsilon of 1/10. So we have this statement from over here that absolute value of f of x minus L is supposed to be less than epsilon. Okay, so let's put that into, see what that means. So that means here f of x minus 5 is less than 0.1. Okay? Now I know it's hard to work with absolute values, so let's try to remove the absolute values. What does it mean for the absolute value of something to be less than 0.1? If I said to you, like, the absolute value of w is less than 0.1, you would know w is between what two numbers? 0.1 and minus 0.1. So this is the same as saying negative 0.1 is less than f of x minus 5 is less than 0.1. Do you agree? That's what absolute value means. So let's see about what that means about f of x. That means f of x itself, if I try to solve for f of x, it means I just need to add 5 to each of these three parts, right? So what will I get when I add 5 over here? 4.9 and 5.1. So in this case, we are given an epsilon. I often think about this. There's like a person on the street who gives us this epsilon. So he is giving us an epsilon of 1/10. That means that we need to make the function stay between 4.9 and 5.1. because those are within 1/10 of our limit of 5. So in other words, if this L is 5, as I wrote it over there, we're allowed to go up to 5.1 and down to 4.9. That's the epsilon band, the epsilon window that the person on the street is giving us. Does that make sense? Okay. So you often think about the person on the street as being an antagonist. He doesn't believe you. He thinks the limit is something else. So in this case, he's going to give us a really narrow epsilon band of just 0.1 up and down, and we have to find a delta. So let's see what this means now. 0 less than x minus 3 less than delta means 0 is less than x minus 3. We're just doing this. There's nothing special about the numbers 3 and 5 and 0.1 and 0.05. I just want some concrete numbers so that this doesn't, to make this a little less abstract, because this is a very abstract definition. So it's saying this is less than 0.5, right? So let's try to figure out what that means about where x would be. If we forget about this 0 for a second, if we want to remove the absolute value, that's saying x minus 3 is less than what? 5/100ths, so 0.05, while also being greater than negative 0.05, right? That's what absolute value means. We'll talk about the 0 in a second here. So that means x is between where and where? If I solve for x there, 2.95, 3.05. So in other words, we're keeping the x. If this is my 3, the x is staying between 2.95 and 3.05. But there's also this extra 0 here. So let's see what that means. What does it mean for the absolute value of x minus 3 to be strictly greater than 0? That means there's one number x can't equal. 3, right? If x were 3, we would have 0 less than 0, which is not true, right? 0 is not less than 0. So this means this, and it means that x does not equal 3. So in this picture, we would often draw like an open circle there to indicate that that point isn't included. And that goes along with what we said last week, right? Because what do we care about? Do we care about the value of the function at 3 or near 3? Near 3. Only near 3. So in fact, if I change this picture and I put a circle here and I put some point up here for the value of the function at 3 or at c, have I changed the limit? No. The limit is still L here, because this point we don't worry about. We said that last week when we were doing our intuitive definition of the limit. And this nice formal definition of the limit now captures that by putting this 0 here. If we didn't put the 0 there, we'd be in trouble, because then that would allow x to equal 3, and then we'd have some trouble staying inside this epsilon band here. So let's just talk one more time about this definition. So we choose epsilon. The person on the street chooses the epsilon. That allows us to go up epsilon units from the limit L and down epsilon units from the limit L. He gives us this band. If we are right that the limit really is L, then we should be able to find some distance away from the C down here so that the graph stays within this epsilon band. And you can see here that I've drawn it, it does, right? We sort of hit the corner perfectly right here, and then by the time we get to this outer side, say call this 3.05, we're still well underneath that epsilon, L plus epsilon there.
So that proves that our limit is 3.
So the question is, does this prove that our limit is 3? If we can prove it, meaning if we can come up with an argument that says no matter what epsilon this fellow on the street picks, I can always find a delta. So remember, he can pick something like 0.0001. All he has to do is make epsilon stay positive. He can make this band as tight as he wants. And if no matter how tight he makes that band, I can find a delta to stay within that so that the function stays within that band, then yes, I will have proved that the limit is indeed what I thought it was, 3. We're not going to prove anything today. We'll prove a limit for the first time next week. But we're just trying to get used to this definition today.
So could he pick something really large?
He could. So if he were in a really generous mood, he could choose epsilon to be 1,000,000. And then we would have this huge, huge epsilon band, and we could probably find a very large delta that would work. But he could also be very in a bad mood, and he could choose some epsilon that's very, very tiny. And we have to be prepared, no matter what epsilon he chooses, to find a delta. So typically, when you do the proof, and we'll do a scratch work for a proof at the very end today, we will discover that the value of delta that we're going to end up using is dependent on the value of epsilon. So we'll come up with some formula for delta that will be like, oh, epsilon over 10 or something like that, so that, because that makes sense, as epsilon gets smaller, so will the delta. Good question. Any other questions before we move on? So now we're going to work on this nice applet that we have. There's a link to it on the course website. This is a GeoGebra applet, free for anyone to use. I'm going to go over here to the computer. Well, maybe I'll come over here. So what we do for this applet is we put in the function here. We put in the value c. So this is example 1 from our handout here. This is a function that we looked at last week. I guess we didn't look at last week. But here's a function. It's got a table of values here in this example 1 handout. And based on the table of values there, what do you think the limit should be? 4. Right? The function is undefined at x equals 1. But when x gets really near 1, the y values keep getting closer and closer to 4. People agree with that? So this limit would be, we think, is 4. So let's try to see how this epsilon delta definition works with this function. So I can put in the formula for the function. I put in the c, where I'm interested in evaluating the limit. C equals 1. I put in the L that I think it is, 4. So you can see it's drawn a horizontal line at 4. And then you put in an epsilon and a delta. So if we think the limit is 4, and the person on the street gives us an epsilon of 0.2, that means he's asking us to stay between what two y values? He's allowing us to go up to 4 point what? 4.2 and down to 3.8, right? So he's saying find a delta that makes the graph stay within 3.8 and 4.2. Now, for the delta that I've got here, 0.4, that means x is starting at 1, going 0.4 back to 0.6, and 0.4 to the right to 1.4. Is that a delta that works? Does this function stay within that epsilon band for all of those x's? It does? No? Let's zoom in a little bit with our cool applet here. So can you see that by the time I get over to whatever this x value is, the y value is now exceeding that upper limit of the band, right? Yeah. And all of these x values down here as well cause y values to be underneath 3.8. We need to stay, we need the y values to stay in this little box here in the center.
On your picture, that didn't happen, or did happen?
On the picture, it did happen because for any x's between here and here, the graph is in this band, right? Do you agree? I mean, starting here, we're within the band, and we're still within the band by the time we get to the far border. People agree with that? So why don't you agree with that? In this case, we're good from here to here. This is within the epsilon band, right? But the x's that we've chosen go all the way from here to here. We chose a bad delta intentionally. I intentionally chose a delta that's not going to work. This delta is too big because all of these y values are too high and all of these y values are too low. So we need to make a smaller delta. So let's try delta to be 0.2. Does that work? Still doesn't work, right? Because it's better, but all of these y values are outside of the epsilon band, as are all of these y values. So let's try delta to be 0.1. So this is 1. Does that seem like it works? In fact, it hits the corners perfectly. You can see that by the time x gets over, so again, if delta is 0.1 and this is c equals 1, I'm staying between where and where on the x-axis, starting at 0.9 and going over to 1.1. And at 0.9, we're exactly at this border, and at 1.1, we're also exactly at that border. And that's OK, because you look, our definition says less than, right? Not less than or equal to. So we don't actually, x can't actually equal 0.9 or 1.1. It can just get very, very close to them. And when it does, the y values do stay within them. So for this particular epsilon and for this particular function, we have found a delta that works. Now, for anytime you find one delta, you can always find infinitely many more. Like, for example, if I go to 0.08, that still works, right? Because now I've even got some extra to spare. The y values are within here and here, always within that epsilon band. So anytime you find one delta, any smaller delta will also work. But all you have to do is find one delta. And often we try to find the biggest delta. So for example, for this one, it would be natural to say delta was 0.1. But if you wanted to say 0.08, that would be fine too. Let's try a smaller epsilon. So now the person on the street is going to be a little bit tougher. So the next thing on the page says to try epsilon to be 1/10. So does our delta still work here? First of all, let's remind ourselves of what's happening. This is L equals 4. He's giving us an epsilon band of 1/10. So we're going from 4 up to 4.1. This is 0.1. So we're going from 4 to 4.1 and down to 3.9. So we want to stay within 3.9 and 4.1. But is this delta working? No, because you can see all of these y values drop below the interval, the epsilon band, and all of these y values drop above. So what do you think I should try for delta? 0.001? Let's not be quite. 0.05? 0.05 hits it, the corners perfectly. So that is, in fact, the biggest delta that will work, 0.05. And again, a smaller delta will also work. So if I make it 0.04, you can see now we make it with room to spare. All you need to find is one delta that works, no matter what epsilon the person on the street picks. Question?
So if you found one delta that works, any value below that delta will also work?
If you find one delta that works, any smaller delta will also work, definitely. Because that just means we're taking an even narrower band. And so if all of these, if between these two x values, the function is where it's supposed to be, then if I take a subset of that, a smaller interval, then it will also be true there. Then the next one is the person is really tough. Now he's going to say let epsilon be 1/100th. So you can see that we are nowhere near. Right? We only stay within the epsilon band for a tiny little bit of time here. All of this is too high. All of this is too low. So now if epsilon is 0.01, we're going between 4.01 on the y-axis and 3.99. That's where he's asking us to stay. He or she, who knows. So let's see. If delta is 0.01, does that work? No, still doesn't work, right? You can see that all of these y values are too high. All of these y values are too low. So what do you say? 0.07? Does that work? That doesn't work, right? We still have some y values over here that are too tall. 0.05. So then we hit the corners perfectly. So this is, in fact, the biggest delta that will work for this function. 0.05. So in fact, you should maybe have seen a pattern, right? In this, for this function, whatever the epsilon was that the person on the street was, how could we find our delta? Take the epsilon and do what to it? When epsilon was 0.2, our delta was 0.1. When epsilon was 0.1, our delta was 0.05. Multiplied by 5/10. Is that a complicated way of saying cut it in half? Yes. Multiply by 5/10. So you can. So as we were saying before, we often end up with the delta being a function of the epsilon, dependent on the epsilon. So in this case, we haven't proven anything yet, but when we do, if we do try to prove this limit, we will end up saying that our delta should always be half of whatever the person on the street gives for the epsilon. But all this is so far is just a number. You'll see that it's a linear function with a slope of 2. So when you go a certain distance in the x-axis, you go twice that distance in the y-axis. Meaning if you go a certain distance in the y-axis, you go half that distance on the x-axis. Any questions on example 1? Okay. So let's look at example 2. This is another function we did last week. If you hit this refresh button over on the upper right corner of the applet, it goes back to where it started. So sine of 3x over x. That's interesting when x is 0, right? Because that's where we're dividing by 0. We thought last week that the limit should be 3. And the person on the street is giving us an epsilon of 2/10. So this is what the graph looks like. But we're really only concerned with what's happening over here. So if the person on the street is giving an epsilon of 2/10 and we think the limit is 3, that means the person on the street is asking us to stay under what y value? Above 2.8 and below 3.2, right? Because just like we did over here with this example, if you do the algebra to solve for that, f of x will be between 3 plus epsilon, 3.2, 3 minus epsilon, 2.8. So is this working? The delta that I've got, delta of 0.4? No, because you can see all of these y values, I drop underneath the 2.8 that I'm supposed to stay above. So that didn't work. Zoom in a little bit. So should I go for a delta that's bigger or smaller? Smaller. 0.3, does that work? No. Does not work, right? 0.25. No, we're getting better, but we still are too low for this little bit over here. 0.2. Yes. In fact, there's even a little bit to spare here, right? We could make delta a little bigger, so I was playing with this on my own. 0.205. Do you see that that still works? Even with a little bit to spare, right? I could even go down all the way touch to here. So we're staying. So you could even make delta a little bit bigger, 0.206 or something like that. But the point is, all we have to do is find a delta that works for this epsilon. So you could go maybe 0.206 or something like that, but 0.205 is good enough. But the person on the street can be as tough on us as she wants or he wants. So now they can change their mind and say, no, I want to go to 0.1. Meaning that now our epsilon band goes from 2.9 to 3.1. Right? We're starting at, we think the limit is 3. The person on the street is giving us epsilon. Remember, we chose epsilon for error. He's giving us an error bound of 1/10 up and 1/10 down from our limit of 3. So is this delta that I've got here working? No, because all of these y values are too low, and so are all of these y values. Notice that we're never even using this part of the epsilon band for this particular function, but that's OK. I mean, all we have to do is stay within it. So should I make delta bigger or smaller? Bigger? Let's make it bigger. That makes things worse, right? We always want to make delta smaller if we haven't gotten a delta that worked. 0.15. pretty close. Hard to see. How about 0.14? Does 0.14 work? Does 0.16 work? No. So 0.14, you could make it a little bit bigger, 0.145 will work. But again, all we have to do is find one delta that works. Often when we're doing the algebra, we end up finding the biggest possible delta. But all we need to do is find one. And in this case, when we stay between these two x values, the y values stay where they're supposed to be. But then the person on the street becomes even more difficult and asks us for 0.01 for a delta, for an epsilon. So our delta is definitely not working, right? Because all of these y values fall outside of the epsilon band, as do all of these y values. So should my new delta be bigger or smaller? Smaller. So what if we cut it in half to 0.07? That work? Still doesn't work, right? We have a lot of y values here that are too low and here that are too low. How about 0.05? Does it work? Not quite, right? If you look carefully, you can see these y values are underneath the epsilon band, as are these.
0.05.
0.04 definitely works, right? We can make it a little bigger, 0.045. That works too, right? And again, we're not proving anything here. We're just trying to get an understanding of this definition. And the order is important, right? The person on the street chooses the epsilon. He gives this vertical band for us to stay within. Once he's done that, we get to choose the delta. In other words, we get to choose which x values we're going to restrict the function to in order to stay within that epsilon band that the person on the street gave us.
We do it on paper, without the computer.
Right.
Do we just plug in the values into the equations?
Well, so as I said, we'll do a so-called scratch work for a proof at the end today. It's going to be involving algebra. So it's going to, we have an equation like this. We want this to be true, right? So we'll know the formula for f of x. We'll know what we think our L is. But we won't choose a specific value for epsilon. We'll just leave epsilon there. And then we'll do algebra to solve for the x's that make that true. Right. So we'll see that at the end. OK, one more example. We also did this one last week, or you guys did, I think. X cubed minus 8 over 2. Remember that one? And that was interesting at x equaled 2. And based on what you guys did last week, you thought the limit was 12. Oops. So now we need to scroll up a little bit. So what, can you see that way that it is? Does the delta that we have work? No. This delta is terrible, right? We're outside of the epsilon band almost all the time. So, and just again, to confirm this, if L is 2 and epsilon is 0.2, the person on the street is letting us go up to 12.2 down to 11.8, right? We have to stay between 11.8 and 12.2. So our delta here was wildly too big or too small? Too big. So let's make it smaller, 1/10. Does that work? No. Half of that, 0.05. Still doesn't work, right? Because still all of these y values are outside of the epsilon band, and all of these y values are outside of the epsilon band. .03. That barely works, right? you can see that, in fact, we have a little bit of room to spare right here and right there. And so, of course, any smaller delta would work as well. But again, all we need to do is find one delta. And the reason for choosing delta is that it stands for difference. So if our C is 2, that means this is x equals 2 down here. And we've chosen a delta of 0.3. That means we're restricting x to go from where to where. If this is 2, x equals 2, and delta is 0.03. From 1.97 up to 2.03. And what this is showing us is that if the x's stay within 1.97, between 1.97 and 2.03, then the y values stay where the person on the street is asking us to make them stay, namely between 11.8 and 12.2. And notice that at x equals 2, this function is undefined. It doesn't show up in this graph. You know, it would be nice if it actually drew a hole there, but the computer just picks a bunch of discrete points and assigns a pixel to each one of them, and it would be sort of a miracle if one of them happened to land exactly on x equals 2, and then there would be a hole there, but it doesn't often happen that way. But the fact that there is supposed to be a hole there doesn't matter to us, remember, because we are saying x minus c has to be strictly greater than 0. So we're not allowing x to equal this number of 2 here. In other words, we're going from 1.97 to 2.03, excluding this one x value, x equals 2 in the middle. But now the person on the street is even more difficult. Cuts the epsilon in half. So is our delta working here? No. This graph looks pretty much like a straight line here, doesn't it? I mean, it's not perfectly a straight line, because if you divide a cubic by a linear function, you should get something in second degree. But we've zoomed in enough, which is a calculus idea, that we'll see that when you zoom in a lot on many functions, they end up looking like lines. So if the person cuts the epsilon in half, what should we do to the delta maybe? Cut it in half. So instead of 0.03, 0.015. That works, right? All the y values are between the epsilon inside that epsilon band. And again, you know, if that one worked, then any smaller one will work. I could use 0.014. Uh-oh, that wasn't so nice. 0.013. I think we're going to have to restart this right now to make that delta come back. All right, technology. So now we learn something funny happens with the applet. So meanwhile, try to see what you think should happen for the very last epsilon that we're looking at. 2. We thought the limit was 12. And now epsilon is 0.01. So the person on the street is extremely strict now. Question?
Did you say that the ratio of epsilon to delta is somehow dependent on the slope of the line?
The ratio, right, because in that first example that we had, the slope of the line was 2.
Right.
And so if you imagine a line with slope 2, whatever distance you move horizontally, you move twice that distance vertically, right? So whatever vertical distance if you want to move a certain vertical distance, half of that horizontal distance will cause that vertical distance. Right? It's sort of the opposite of how we usually think about slope. Usually we think a slope of 2 means if you go a certain distance in the x, you go twice that in the y. But you can also think about it the opposite way. If you go a certain distance in the y, you go half that distance in the x direction. Right. So here this delta is not working, right? It's much too big. So how about 0.05? You're way too optimistic. Does that work? No. 0.04. 0.004 is what I meant. 0.003. No. 2. I think it doesn't work, right? You can just see a tiny little bit here where the graph falls underneath and a tiny little bit there. So how about 0.015? That one works. And so then, as we said, anything smaller will work as well. 0.014, 0.013, they all work. Any questions on the applet? So nothing what we just did proved anything. We didn't prove any of these limits are anything. We just looked for each case at 3 different values of epsilon, and for each one we found a delta that would work. At least we thought it worked based on the graph, but that's not a proof. A picture in this case is not a proof. So what we really need, if you want to prove something, we have to come up with a way that no matter what epsilon the person on the street gives us, we have a recipe for finding the appropriate delta. So as many proofs go, you don't just start off and write the proof. You need to do a bunch of scratch work in advance, and then you write the proof. So that's what we're going to do for a not very exciting function here. So this is example 4 on the handout. We have the function f of x equals 4x minus 3. And we're trying to compute the limit as x goes to 2 of this function. Now this function is really much more boring than the ones we looked at last time because it doesn't have nothing undefined or anything like that, right? In fact, it is a line, doesn't have any holes or anything like that. So as x gets closer and closer to 2, as you plug in y values closer and x values closer and closer to 2, what should the y values get closer and closer to? 5, right? So the first thing we do next week is actually going to be writing the proof of this. But before we can write the proof, we have to do this scratch work, as I call it. And the scratch work involves starting with where we want to get in the definition and working backwards. And then the proof will involve doing these steps in the opposite order. So what do we need to find? So the person on the street gives an epsilon, and it's up to us to find a delta, right? Such that if, so then let's go back to our definition over here. And this is all on the handout here on page 3. You don't have to write down all these things. We have to find a delta greater than 0 such that if 0 is less than absolute value of x minus what for us now? What are we using for c in this problem? 2. So 0 less than absolute value x minus 2 less than delta, then absolute value of f of x, right? So that's this part. Then f of x minus L, and what are we saying L is here? 5 will be less than epsilon. So if we look at this as a picture, our function 4x minus 3 is just looking like this. Oops. And here we are at x equals 2. We think the limit is 5. So the person on the street gives us an epsilon band. So the person on the street says you can go up this high and down this low. In other words, we can go up to 5 plus epsilon and down to 5 minus epsilon. That's the epsilon band that this lady or gentleman out on the street is asking us to stay within. And we can do that as long as we find a suitable delta. And so if you look here, it looks like if I go down like that and down like that, 2 plus delta, 2 minus delta. So if I've drawn the graph correctly, it seems like we should be able to do this. Right? No matter what epsilon the person picks, no matter how narrow this band is, I can pick a narrow little set of x values so that the y values stay in that epsilon band. Now let's do the scratchwork algebra to see that. So in all these scratchwork proofs, you start with where you want, all these scratchwork, you start with where you want to end and work backwards. So we want to end with this. So we say f of x minus 5 less than epsilon is the same. And so in math, when I draw this double-headed arrow, not just double-headed, but double-barred as well, that is the mathematical symbol for saying that two statements are exactly equivalent. Sometimes people read that as if and only if. It means these two statements mean exactly the same thing. So what is my f of x? What's my formula here? In this particular example, the function f of x is what? 4x minus 3. So I can just replace that f of x by 4x minus 3 minus 5 is less than epsilon. So again, this double-headed arrow means the statements mean exactly the same thing. That is to say, the set of x values that satisfy this equation are the same as the set that satisfy this equation. I guess they're not equations, they're inequalities. The set of x's that make this inequality true are exactly the same as the set that make that inequality true. And often in these, you sort of just follow your nose. Just do the thing that seems like the natural thing to do next. So algebraically, what would you do inside these absolute value bars next? We want to simplify that. We could write it as what? 4x minus 8, right? And now remember, what is it that we have control over? What we have control over is this thing, absolute value of x minus 2. Right? We choose a delta that controls the size of this. Remember, x minus 2 in absolute value is the distance x moves away from 2. So I have control down here in the distance x moves away from 2. So somehow in there, I'm hoping to find an x minus 2 hidden. So do you see an x minus 2 hidden in that formula there? Or that expression, I should say. Do we divide it by, or factor out a 4? If we factor out a 4, then I see an x minus 2. Convenient how that happened, isn't it? So we knew to look for that because of what the definition says. So I would like to get just an x minus 2 by itself. So somehow I want to get rid of that 4, right? Divide by epsilon?
Epsilon divided by 4.
Okay, so we're going to end up with epsilon over 4. Let's do that in 2 steps, though, because we want to be, I've learned in teaching the seminar a lot of times that there are a lot of ways to mess up absolute values, understanding of absolute values. Somehow absolute values aren't taught so well, so we're going to be really careful with absolute values. So there's a property of absolute values that's useful here now called the absolute value of a times b is the same as the absolute value of a times the absolute value of b. This is a useful property of absolute values. You can verify it on your own. Meaning I can rewrite this as absolute value of 4 times absolute value of x minus 2 less than epsilon. So now I've got an absolute value of x minus 2 all by itself, just as we were hoping to get. So we did in 2 steps what Phil was suggesting we do in 1. So x minus 2 less than. But then saying absolute value of 4 is really just the same as saying 4, right? The absolute value of 4 is 4. The absolute value of a positive number is itself. So absolute value of x minus 2 is less than epsilon over 4. So we've ended up with exactly what we wanted. X minus 2 less than some quantity. In other words, so choosing delta to be epsilon over 4 should work. The proof of that, as I said, will come next week. Robert, watching online, I agree with what you've got there. Sorry, I didn't look at the chat room when we were doing the applet. I didn't want to have them both on the screen. And so the proof of this will come next week, but I just tried to give us a specific example here. So let's suppose if epsilon, if the person on the street gives an epsilon of 0.1, what would we choose our delta to be? We choose, so what we have found a recipe for what the delta should be. So whatever the person on the street gives for the epsilon band, we cut that we divide that by 4. So then we should divide this by 4 and get 0.025. So then what does 0 less than x minus 2 less than 0.025 means? That means x is going to be between where and where? I'm starting at x equals 2, and I'm going 0.025 in each direction, right? So we're going to go back to 1.975. So the x has to stay above 1.975 and below 2 point what? 2.025. But this 0, as we said earlier, means that x cannot equal what? 2. Now, in this particular function, there's no problem with x being 2, right? Because this graph is continuous, so the value of x at 2 is 5. But as we said last week, we don't care what happens at 2, we only care what happens near 2. So if this were one of those functions where there was a circle here and the point was absent or the point was somewhere else, then we'd need to take advantage of that. But we don't have to. So that's what that part means. And then, so what are the values of f of x? So f of 2.025. In other words, if I plug this endpoint in, f of 2.025, that means I'm taking 4 times 2.025 minus 3. Without doing the calculation, can you guess what we're going to get? 5.025. Not 5.025. We're going to hit the corners perfectly here. The epsilon that we were given as an example was 0.1, right? So he's asking us, on the person on the street, if epsilon is 0.1, we're supposed to stay below 5.1 and above 4.9. And so you can actually confirm that when you plug this in, you will in fact get 5.1. And when you check the other endpoint, f of 1.975, you get 4 times that minus 3. And no great surprise, that's 4.9. And each of these exactly 0.1 from our limit L equals 5. Meaning we hit the corners perfectly in this example. And that's, again, because this is actually a linear function. So let's just confirm this graphically with our applet. Anyone need to give you a minute to write that down? not very exciting. Projector on. Oh, got to push one more button, I think. There we go. So I have put in our new function, 4x minus 3. We're looking at x approaching 2. We thought the limit was 5. And we just looked at a specific example of epsilon being 1/10. But you can see that the delta that is there is too big, right? We were supposed to choose delta of what? 0.025. So now let's zoom in on that. And look at that. We hit the corners perfectly, right? Because when x is 2.025, the y value of the function is exactly 5.1. When x is 1.975, the y value of the function is exactly 4.9. And so getting back to what Bill was saying before, the slope of this graph is 4. So if we go a certain distance in the x direction, we go 4 times that distance in the y direction. And that explains why the recipe that we figured out on the board in our scratch work was look at the epsilon that we're given and divide it by 4 to figure out the delta. Whatever vertical distance we're given to play around with by the person on the street, if we use a horizontal distance 1/4 that, then we'll be guaranteed to stay within the epsilon band that he's given us. Do you like it?
I wouldn't go that far.
So there's a lot going on with this definition, right? In addition to the complicated Greek letters, all these different things are happening. Our goal today was to just try to get an understanding of what the definition is, what it's telling us, and how it works. Question?
Is this what Cauchy came up with?
This is what those nice guys back then, Cauchy and Weierstrass and Bolzano, came up with in the early 19th century.
Professor, actually, the epsilon and the delta, they were looking too intimidating.
Yes.
They're reading.
Because they were Greek letters?
But now you make them to look friendly.
Okay, good. I'm glad that the epsilon and delta have become friendly. I agree. It is an intimidating definition with these Greek letters. But again, the reason that epsilon was chosen is because it's like our letter E for error. So the person on the street gives you some error bound that you have to stay within. You know, like when you're manufacturing some product, you have some error tolerance that you can stay within. And if you don't stay within it, then you have to reject that particular production of the item. And then the delta is standing for difference because we're going a certain difference, a certain distance from the x that we're centered at. So next week, we will actually prove something. So the first example we're going to look at next week will be to try to prove that this limit is 5, what we think it is. And the proof of that will basically be doing the scratch work backwards. Because we will say, OK, the person on the street gives us an epsilon. What do? We choose a delta to be 1/4 of whatever that person gave us. And then we start with the first. We're trying to prove something of the form if P, then Q. So if you're trying to prove a statement of the form if P, then Q, you start by assuming the P part to be true. You do enough logical steps to land at the Q part, and then you've proved it.